Hello everyone, this is Mirzai from Cal Poly Pomona, and in this lesson we are going to learn how to find a feasible solution for a transportation problem. First, let's look at the definition of a transportation problem. There is a class of optimization problems that can be solved using an easier version of simplex method. Because it's mostly used to solve the problems involving allocation of product resources to product destinations, this type of problem is frequently called transportation problem. For example, allocation of power from different power plants to different cities to minimize the total transmission cost is a transportation problem. Usually there is a cost table associated with a transportation problem. An example of a cost table is shown here. The number inside each cell shows the cost for transmission of a unit of power from each plant to each city. The number in the right-hand side of the table shows the maximum capacity of each plant, and the number in the bottom of the table shows the minimum demand of each city that needs to be met. Having the transportation, or better said, the transmission cost from plants to the cities, as well as the city's demand and plant's capacity, we can formulate this problem. If you were about to formulate this problem in a way that it minimizes the total transmission cost, what would you define as your decision variables? You can pause this video and try to formulate this problem. Earlier, we mentioned that the number inside each cell shows the transmission cost of a unit of power from a plant to a city. For example, if I transfer 1 unit of power from plant 1 to city 1, I have to pay $8. So the cost of transmitting 1 unit of power from plant 1 to city 1 is going to be $8. If I transmit 2 units of power, I have to pay 2 multiplied by 8, which is $16. If I transfer X unit of powers, I have to pay $8x to transmit the power. So we define the decision variable of this problem to be the amount of supply from plant I to city J, and we show it with xij. Using this decision variable, we can define the objective function, which is shown here. In a transportation problem, we usually have 2 sets of constraints, one set for demand and one set for supply. First, we want to make sure that each plant is not providing power more than its capacity. So the first plant capacity constraint should be formulated so that the summation of power provided from plant 1 to all customers, which is the first row, doesn't exceed the plant capacity, which is 45. So the constraint for the first plant supply will be the summation of the power provided to customers is less than or equal to 45. The same applies for the second as well as third plant. As you see here, for each row we have written supply constraint. This set of constraints is often called supply constraint. Additionally, we have to make sure that the demand requirement of each customer is met. Because the summation of variables in a column shows the total power provided to each customer, this time we have to write a constraint for each column of the table. Therefore, city 1 demand constraint is going to be the summation of the decision variables greater than or equal to 45, because this demand is the minimum requirement that we have to meet, but it's okay if we provide more than 45 for the customer 1. So we have to write one constraint for every column of this table. This set of constraint is called demand constraint. And at the end, all the decision variables also have to be positive. This problem is a typical linear programming problem that we have constraints with greater than or equal as well as less than or equal signs. So to solve this problem, we have 2 options. First, we can use Big M or two-phase method that we learned earlier. But there is an easier method of simplex that we can use to solve this problem. This method works in 2 steps. First, we have to find a feasible solution to the problem. We have 3 different methods for finding a feasible solution to this problem. One is northwest corner method, second is minimum cost method, and third is the Vogel method. After finding a feasible solution to this problem using one of these methods that we're going to learn in this lesson, we have to improve this initial feasible solution to an optimal solution. So we have to iterate and improve the result. The only difference with this method and the regular Big M or two-phase method is it reduces the computational effort. We don't need to calculate the table for all the decision variables. So in this lesson, our focus is on part A of this method, which is finding a feasible solution. We're going to learn 3 methods to find a basic feasible solution for a transportation problem using the northwest corner method, minimum cost method, and Vogel's method. Again, remember, this initial feasible solution is not an optimal solution, and later in a separate video we learn how to iterate and improve this initial feasible solution to an optimal solution. So let's first look at northwest corner method. Assume that we are trying to find a basic feasible solution to this transportation problem. Before solving any transportation problem using this easier version, we have to make sure the problem is in a balanced form. So the first question is this problem a balanced problem or not? A balanced problem is a problem in which you have demand equal to supply. As you know, the numbers in the right-hand side of this table show the supply, and the numbers in the bottom of this table shows the demand. So the total supply for this problem is 155, 45 plus 60 plus 50. Also, the number in the bottom of this table shows the demand, which if we sum them all, you get 155. So the demand is equal to supply. Yes, it is a balanced problem. If the demand is greater than supply, then we don't have a feasible solution for this problem because your supply is already less than your demand, so there is no way that you can satisfy all the demand existing in the problem. However, if your supply is more than demand, then there is a chance to get an optimal solution for this problem, but we have to adjust our table and do some manipulation in the table before we move on to finding a feasible solution for this problem. For now, we're not going to talk about the adjustment of the table. We assume that our table is balanced and we move on with the balanced example that we have here. Later we discuss this case and the manipulation that we have to do to solve the problem. So first, let's learn how northwest corner method works. Assume that we have this transportation table with the transportation costs inside each cell. The supply is provided in the right-hand side of this table. The demand is given in the bottom of this table, and our job is to find a basic feasible solution for this problem using the northwest corner method. So in the northwest corner method, you have to start from the northwest corner of this table. The northwest corner of this table is this cell. Now, we have to see what is the maximum amount that we can provide for the city 1 from the plant 1. Basically, in this case, we are looking at the minimum of the supply and demand, because the minimum of the supply and demand is what actually can be provided to customer 1 through plant 1. So the minimum amount in this case is equal to 45. What happens is now the supply of the plant 1 has been allocated to customer 1, so it will reduce to 0. There is no more capacity available for plant 1. Also, the demand of the customer 1 is satisfied by 45, so there is no demand left from customer 1, which is not met. So systematically, when we start from the northwest corner, we find the minimum of the supply and demand for its associated row and column, and then we reduce this minimum amount from the supply and demand. So basically the minimum of 45 and 45 goes here, and we reduce the 45 from each side of this table. Now, since the plant 1 and city 1 are exhausted in terms of their capacity and demand, we eliminate those from our table. If I do this, the first row and the first column will be eliminated. Now we have to repeat this step again. We have to find the northwest corner in the remaining table. In the remaining table, which is in this area now, we have to find the northwest corner. Now I have to find the minimum of supply and demand for this cell. So it's in fact the minimum of 30 and 60. This value is 30. So we put 30 here, and then we reduce 30 from supply as well as demand. That gives me 30 here and 0 here. Now, since the demand for customer 2 is exhausted and has reached to 0, we eliminate this column. But here, since our supply is still a positive value, it means that we still have capacity in the plant 2 to satisfy some demand. We don't eliminate it from the table. So every time you reach 0 for supply or demand, you eliminate it from the table. Otherwise, you keep it. So let's move on to the next northwest corner, which is this corner. Now we have to find a minimum between 40 and 30. The minimum of the two is 30, so we reduce the 30 from the supply as well as the demand. This time the plant 2 has been exhausted, so we eliminate plant 2 from the table. And we continue finding the northwest corner in the table. The new northwest corner in the remaining table is this cell. And now we have to find a minimum between 50 and 10. The minimum value is 10, so we put 10 here and we reduce 10 from both supply and demand associated to this cell. Now customer 3 has been exhausted, so we have to eliminate this column and move on to the next northwest corner, which is the last cell of the table. Now if I find the minimum between the demand and supply, since it's a balance problem, at the end you're always getting the same amount for your last table. So we have 40 and 40, the minimum is 40, and we have to reduce that amount from your demand and supply. So this is the final solution to your problem. So X11 is the amount of supply from plant 1 to customer 1 is 45. The amount of supply from plant 2 to customer 2, or X22, is 30. X23 is 30. X33 is 10. And you have X34 equal to 40. Now we can calculate the total value of objective function. So if I supply 45 units from plant 1 to city 1 and its associated cost here is $8, I just need to multiply that by 8 to calculate the cost of transmitting power from city 1 to plant 1. So with this logic, your total transmission cost for this feasible solution is going to be $1,470. Please note that this is not an optimal solution to your problem. This is just the basic feasible solution to start your simplex table. But instead of using the typical simplex table, we're using an easier version of the simplex table here. So this is just the beginning to your simplex table. But we're not going to talk about optimization of a feasible solution in this lesson. Later we will see how we can take this initial feasible solution and improve it to an optimal solution. Another point that you have to pay attention is that the northwest corner method works independently of the transportation costs. What does that mean? So if at the first place I gave you a table like this, you would have been able to solve this problem using the northwest corner method, not having the transportation costs inside the table. Because in this method, we just go after the northwest corner of the table and we don't really take into account the transportation costs that we had. One of the methods that takes into account the transportation costs to find a basic feasible solution is a minimum cost method. Let's look at the same problem, but this time instead of northwest corner method, we're going to solve it using the minimum cost method. So we have the same transportation table with the cost given inside the table. This time, instead of picking the northwest corner, we're going to find the cell with the least cost. In this example, this is the cell with the minimum cost. I'm looking to find the minimum of all these transportation costs that is given inside the table. So if I look at all of these numbers, the minimum is related to the cell 3 and 4, and the next step will be very similar to the northwest corner method. We have to find the minimum of supply and demand for that cell and then reduce it from the column and the row associated with the cell, and then eliminate the column that is exhausted. So here our city 4 demand has been exhausted, so we eliminate it from the table. Now I have to find the cell with the minimum transportation cost in the remaining table. This time the cell with the minimum cost is this cell. Now I have to find the minimum of the supply and demand for this cell. The minimum of the two number is 30. So I write 30 here and then I reduce the value of 30 from the demand and supply. This way, the customer 2 demand gets exhausted, so we eliminate the column related to the customer 2 from the table, and we continue the minimum cost method by finding the minimum value in the remaining of the table. So this time, 8 This cell has the minimum cost. Again, we have to find the minimum between the demand and supply related to the cell, which is 15, and then reduce 15 from both column and row. And as you see, this time plant 1 capacity gets exhausted, so we eliminate the first row from the table. Now we have to find the minimum cost in the remaining of the table. This time the minimum cost is related to the cell with a transportation cost of 9. Now I have to find the minimum between the supply and demand related to the cell, which is 30. So I copy 30 here, and I reduce 30 from the demand and supply. And since the demand related to the first customer gets exhausted, I eliminate it from the table. Then I have to find the minimum cost in the remaining table, which is related to this cell. I have to find the minimum of supply and demand for this cell, which is 30. I copy 30 and I reduce 30 from both demand and supply. This time supply for the second plant gets exhausted. We eliminate it from the table, and we are left with 1 cell and demand and supply of 10. This condition happens because in the first place we had a balance problem, so we're having the same demand and supply for the very last cell. We copy that and we reduce 10 from both supply and demand, and we have found a basic feasible solution to our problem with this operation. Now I mentioned that for the last cell we get to the point that the supply and demand is always the same because we are looking at a balance problem. If we didn't have a balance problem in the first place to start with, we had to do some manipulation and we wouldn't get the same supply and demand at the end. We're going to talk about unbalanced problem later in this course. So the value of the decision variables are 15 for x11, 30 for x12, and x21 is 30, x23 is 30, x33 is 10, x34 is 40. Please note that the orange value are the actual value of decision variables and not these values that are in a box. Those are the transportation costs. Also, the value of decision variables that their related cell is empty is equal to 0. They are the same as the non-basic variable in a simplex table. So if we put this in a context of simplex method, the positive values are our basic variables, and the decision variables that their related cell is empty, their value is equal to 0, or they are our non-basic decision variables. The total value of the objective function is 1320. And to calculate this value, I multiply the value of decision variable by its associated transportation cost. It's basically 8 multiplied by 15 plus 6 multiplied by 30 plus 9 multiplied by 30, 13 multiplied by 30, 16 multiplied by 10, and 5 multiplied by 40. So let's look at this example, but this time we're trying to solve this example using Vogel's method. So the problem is find a feasible solution for the following transportation problem using the Vogels method. In the Vogels method, instead of going after the minimum value or minimum cost inside the transportation table, we are defining a term called penalty value for each row and each column. Penalty term for each row and each column will be the difference of the first and second minimum cost of each row and each column. So for example, for the first row here, we are interested in finding the difference between the first and second minimum value of this row. The first minimum value is 6. After 6, the minimum value is 8. So the penalty cost associated with this row is 2. And for calculating the penalty cost, we always consider the absolute value. So we don't consider negatively, just looking at the difference between the two numbers. Then for the second row, the first minimum value is 7, the second is 9. So the difference between them is 2. For the third row, the first minimum is 5, the second is 9. So we are looking at 4 for this table. Let's calculate the penalty values for each column. For the first column, the first minimum value is 8, the second is 9, so associated penalty cost, which is the difference between the two numbers, is 1. For the second column, the minimum is 6, the next minimum is 9, the difference between the two is 3. In the third column, the minimum is 10, the second minimum is 13, the difference between the two is 3. In the fourth column, the minimum is 5, the second minimum is 7, the difference between the two is 2. Now we have calculated all the penalty costs. We can continue to solve this problem using the Vogels method. In the Vogels method, we start with the row or column that has the maximum penalty cost. The maximum penalty cost that we have calculated here is related to 4. So we have to start from the row associated with this penalty cost, which is the third row. Now in this row, we have to find the cell with the minimum transportation cost and start allocating our resources to that cell. In this row, as you see, this cell is associated to the minimum cost, which is 5, and we have to start allocating our resources to this cell. So the minimum of the demand and supply here is 40. So we put 40 here and we reduce it from both column and row. Now, again, we have to implement the same step as the minimum cost method. We have to get rid of the column or row that is demand or supply is exhausted. Here, since this demand has been exhausted, we eliminate that from the calculation. Now we have to update our penalty cost because one column has been eliminated, so the penalty cost here needs to be updated. Whereas for the penalty cost of each column, you don't need to adjust anything because we didn't make any change in the first 3 columns. The only thing that needs to be updated is the penalty cost associated with each row because the elimination of the last column is going to impact the penalty cost that we have calculated. So again, if I look at the first 2 minimum value of the first row, I have 6 and 8, so the penalty cost associated with them will be 2. For the second row, the first minimum is 9, the second is 12, the difference between them is 3. For the last row, the minimum is 9, the second minimum is 14, the difference between them is 5. Since the penalty cost of each column doesn't change by eliminating the first column, I'm just going to copy them for the next step. Now that we have updated the penalty cost, we have to repeat the same step as the first round. We have to find the maximum value of the penalty cost, which is 5, and find the row or column associated to that number. This time we have a row, so the row associated with this penalty cost is the third row. Then in this row, we have to find the cell that has the minimum cost, which is 9. Now this is the cell that we are going to use for the allocation of resources. The minimum between 30 and 10 is 10, so we copy 10 here and we reduce 10 from both demand and supply associated with that cell. And now we have to remove the column or row that is exhausted. This time the third row is exhausted, so we eliminate this row and we continue the Vogels method with the remaining of the table. So as you see, nothing will change in terms of the penalty cost of the first and second row, but by eliminating the last row, the penalty cost of the columns is going to be updated. So let's update the penalty cost here. We're just left with 2 numbers, so simply the difference between the two gives us the penalty cost for each column. The difference between 8 and 9 is 1, 6 and 12 is 6, 10 and 13 is 3. Now that we have updated the penalty cost, again we have to repeat the same step, finding the maximum value of this set of number, which is 6, and in the related to this maximum value we have to find the minimum cost. The minimum cost is related to this cell, which is 6, and then we have to find the minimum of supply and demand for this cell, which is 20, reduced from the row and column related to this cell, and then eliminate the exhausted cell. We have to continue with the leftover of the table, which only has 4 cells. We have to update the penalty cost for each row because by eliminating the second column here, our penalty cost is going to change. So if I update the penalty cost for the first row, is the difference between 8 and 10, which is 2. For the second row, it's the difference between 9 and 13, because these are the only things that are left in our table. The penalty cost associated with the first and third column doesn't change, so we just copy them here. Now we have to find the maximum number among 1, 3, 2, and 4. The maximum is associated to the second row. In the second row, we have to find the minimum cost, which is the cell with cost of 9. So we allocate the minimum of supply and demand and then reduce that 45 from both supply and demand, where we eliminate the column that is exhausted here. Now we are left with only two cells. So if I want to calculate the penalty cost for the first and second row, I cannot do that because we don't have two numbers to calculate the difference between the two numbers in these rows. So there is no penalty cost for those, and there is a 3 penalty cost for this column here. The maximum will be associated to this column. So we have to look for the minimum value in this column and allocate our resources. So the minimum between 10 and 13 is 10. So we have to allocate the minimum of 40 and 25 to this cell. The minimum is 25. So I put 25 here. This way I will reduce this 25 to 0 and 40 becomes 15. Now, since the capacity related to the first plant is exhausted, I can eliminate it from the calculation. I'm left with only one cell, and the minimum of 15 and 15, as you see, this 15 and 15 here is 15 that will be allocated to this cell, and I have to reduce it from the supply and demand here. So with this, we're finished with calculation of our decision variables. Now we can write their values. We can also calculate the value of objective function, which is the summation of the products of the decision variable values and their associated costs. So it's going to be 6 multiplied by 20 plus 25 multiplied by 10 plus 9 multiplied by 45, 13 multiplied by 15, and 9 multiplied by 10, and 5 multiplied by 40. So if you look at the value of objective function, it's 1260. Couple of notes here. So as you see, the value of objective function in this case and the previous two examples are not the same. From the northwest corner method, the value of objective function is 1470, and from the minimum cost, the value of objective function is 1320. And from the Vogels, we obtain 1260. So you see the value of objective function in the Vogels method is better than the minimum cost, and minimum cost is better than the northwest corner. But this condition doesn't always happen. Sometimes you might get a better objective function in a minimum cost than in your Vogels method, because none of these methods is actually an optimal method of finding a solution to a transportation problem. They all provide a basic feasible solution, but since the northwest corner method doesn't consider the cost of transportation to find that basic feasible solution, it usually has a higher cost at the end in comparison with Vogels or minimum cost that takes into account the transportation cost of the table. Now let's look at one example of unbalanced transportation problem. In an unbalanced transportation problem, the amount of supply and demand are not the same. For example, here the total supply is equal to 165, whereas the total demand is 155. So for this problem, we can find a feasible solution because the demand is less than supply. But if the situation was the opposite way, your supply was less than your demand, then you couldn't find a feasible solution to this problem. There isn't not enough capacity to meet all the demand in the first place. Now, in this case, since the supply is higher, we can find a feasible solution. So we have to adjust this table before we can use any of the methods that we learned earlier, such as northwest corner, minimum cost, or Vogel's method. So let's see how we can adjust this table. The way that we adjust this table is adding a dummy customer to the system, and the demand for the dummy column is going to be equal to the difference between the supply and demand. Obviously, since we're adjusting the table for the cases that supply is greater than demand, you're going to have a positive value all the time because we assume that this is the condition where supply is greater than demand. So in this case, we're going to have 10, and using this dummy column, now we have a standard table that we can use any of those methods that we learned earlier, such as northwest corner, Vogels, or minimum cost. So we associate the cost of 0 for transporting anything from plants to this dummy customer. So since it doesn't exist, all the transportation costs are 0 here. For example, if I'm solving for a Vogel's method, the penalty cost for the first row will be the difference between the refers to minimum value. So the difference will be between 0 and 8. So the penalty cost for this row will be 8. So is the same for the second and third row. So you actually account this dummy customer like an actual customer in the system, with the difference that its cost is 0. So if I'm solving for a minimum cost method, the first step when I'm looking for the minimum cost, I can choose any of these cells as my initial assignment, because the costs associated with these cells are 0 and they are my minimum value. So every time in a transportation problem that you run into a tie, it doesn't matter which one I choose to continue the problem, you always have the option of choosing either one of the cells to continue the problem. With this, our lesson has concluded. Please refer to the blackboard for your assignments. Thank you.